Linear search, also known as sequential search, is one of the simplest and most fundamental searching techniques used in computer science. It is an algorithm that checks each element in a list or array one by one until the desired element, known as the key or target, is found. If the element is located, the algorithm returns its position. Otherwise, it concludes that the element is not present in the list. The simplicity of linear search makes it the first algorithm taught in introductory programming courses and a foundational concept for understanding more advanced searching techniques. The linear search algorithm works by starting at the first element of the list and comparing it with the target value. If the current element matches the target, the search is successful. If it does not match, the algorithm moves to the next element and repeats the comparison. This process continues until either the value is found or the algorithm reaches the end of the list. Since it checks each element sequentially, linear search does not require the data to be sorted. This is one of its biggest advantages, as it can be applied to both sorted and unsorted datasets without any modifications. Linear search is easy to implement and understand. The logic is straightforward and requires very little programming experience. A common example appears in arrays, where each element can be accessed by its index. In such cases, the algorithm iterates through the array using a loop and compares each element to the target value. Because of this simple structure, linear search is often used in applications where the data set is small or the search operation is performed only occasionally. Its performance is predictable, making it useful even in real-time systems where consistency is more important than speed. However, linear search is not efficient for large datasets. The time complexity of the algorithm is O(n), meaning that in the worst case, the algorithm must examine all n elements. For example, if the element being searched for is at the end of the array or not present at all, the algorithm makes the maximum number of comparisons. This can severely impact performance when dealing with large lists. Because of this limitation, more efficient algorithms such as binary search or hash-based searching are preferred when working with large volumes of data. Despite its inefficiency with large data sets, linear search has several advantages. It requires no pre-processing or additional memory, making it suitable for simple hardware and low memory environments. It is also safe to use with complex data structures where random access is not possible. For example, in linked lists, where elements are accessed sequentially, linear search is often the only practical option. It is also robust and works well even when the structure of data is irregular or unpredictable. Linear search remains an essential concept in algorithmic study, forming the basis for understanding more advanced search techniques. Its simplicity, flexibility, and universality ensure that it remains relevant in many areas of computing, even as more sophisticated algorithms are developed. By learning linear search, students and programmers gain a strong understanding of iteration, comparison, and performance trade-offs, which are key concepts in algorithm design and analysis.